So today we will discuss the calculational part of the theory of relative velocity. Okay. So in the previous 11th video and 12th video, it was shown that displacement of point P in a given time interval depends on the frame of reference, and that's why velocity, acceleration and trajectory of P with respect to different frames are not the same. So today our main aim will be to discuss how the velocity of point P are interrelated in two different frames which are in mutual rotation in general case, and how acceleration of point P in two different mutually rotating frames are related to each other. This will calculate, okay, this today will calculate. So first of all, see, suppose this is a reference frame F, okay, and P1 and P2 are 2 points. P1 and P2, R is the vector from P1 to P2 at time t. So R will be called the relative vector of P2 with respect to P1. R will be called the relative vector of P2 with respect to P1. Suppose velocity of P1 with respect to F frame is V1F at time t, and velocity of P2 with respect to F frame is V2F at time t. Assume that O is some base location of frame F. O to P1 is vector R1 and O to P2 is vector R2. Okay. Now we know from triangle law that R2 is equal to R plus R1, triangle law of vector addition. So R2 is just equal to R1 plus vector R. And this vector equation is valid for all times. Now suppose we derivate this vector from both sides with respect to time t. dr2 by dt in frame F is equal to dr1 by dt in frame F plus dr by dt in frame F for all t. So this we have already explained in the 9th and 10th videos that whenever we take the time derivative of a vector, we should specify the name of the reference frame. Without that, there is no meaning. Okay. So here F means that we are taking the time derivatives in frame F. Now this quantity is known to be V2F, velocity of P2 with respect to frame F at time t. And this quantity is taken to be V1F, velocity of P1 with respect to frame F at time t, plus dr by dt in frame F for all times. So from this equation we can see that dr by dt in frame F is nothing but V2F minus V1F. So this quantity V2F minus V1F is called the relative velocity of point P2 with respect to point P1 in frame F. Relative velocity of point P2 with respect to point P1 in frame F. Relative velocity of point P2 with respect to point P1 in frame F, V2F minus V1F, which will be denoted in short notation as Vp2P1 slash F. Vp2P1 slash F, velocity of P2 with respect to P1 in frame F, slash meaning in frame F. And R is the relative vector of P2 with respect to P1 at time t. R is the relative vector of P2 with respect to P1 at time t. So dr by dt in frame F वही Vp2P1 slash F हो गया. So Vp2P1 slash F is equal to V2F minus V1F, that is the relative vector of P2, time derivative of the relative vector of P2 with respect to P1 in frame F. So Vp2P1 slash F is equal to V2F minus V1F, and that is equal to dr by dt in frame F. Fine. I love it, okay. But one thing will explain, here one thing should be clearly understood. Whenever we find the relative velocity of between 2 points, we have to specify the name of the frame. Without specifying the name of the frame, it is meaningless. For just to make this concept clear, why we mentioned frame F? See, suppose, so this is the question, why frame F mentioned? This is generally not seen, no? Whenever you see relative velocity between 2 points, we say V2 minus V1. We don't say V2F minus V1F here. We don't say V2M minus V1M. We simply say V2 minus V1. That is not correct. You have to specify. See, relative velocity between 2 points is the difference in velocities of P2 and P1. But velocity depends on the frame of reference. So relative velocity between 2 points also depends on the frame of reference. If you don't specify the name of the frame, V2 minus V1 has no meaning. I just make it clear by example. Okay, see. So why relative velocity in frame F? In frame F meaning I am explaining. Yeah, in frame M. And why this name of the frame clause, why is it coming here? This I would like to explain. See, so why name of the frame? Why name of the frame? That is the problem. That is the question. See, I'll take an example. Imagine that we have a rigid rod. Okay. Suppose its lower end is flexibly joined to the ground frame. This is the rod taken to be a rigid body denoted by R, say. And G for ground frame. G meaning ground frame. Lower end of rod is flexibly joined to the ground. It's a flexible joint. Okay. Suppose P1 and P2 are the two material points of the rod. P1 and P2 are the two material points of the rod. Vector from P1 to P2 is vector R. R is the vector from P1 to P2. Fine. R is the vector from P1 to P2. Suppose this is the situation, say at time t. Alright. Now what happens? Suppose with respect to rod, with respect to ground, the rod turns. So say at time t to t plus dt, this rod turns like this. Anti-clockwise turn. Rod has turned anti-clockwise with about this lowest point pivot, flexible joint. So at t plus dt, P1 will come here, P1 dash, and P2 will come here, P2 dash. See, if we see one thing, suppose the angular speed of rod is omega, okay, and suppose distance of P1 from the pivot is L1, and distance of P2 from the pivot is say L2. L1 is the distance of point P1 from the pivot, and L2 is the distance of point P2 from the pivot. Omega is the angular speed of rod with respect to ground. See, if we take the relative velocity of P2 with respect to P1 in ground frame, see, if we write Vp2 P1 in rod, then that definition will be V2 rod minus V1 rod. This meaning what? Velocity of P2 with respect to rod minus velocity of P1 with respect to rod. But P1 and P2 are the material points of the rod. So since P1 and P2 are material points of the rod, so velocity of P2 with respect to rod is 0. So this is 0. And P1 is also a material point of the rod. So its velocity with respect to the rod itself is also 0. This minus this is equal to 0 minus 0, that is 0. Velocity P to P1, P to P1 with respect to rod is 0. So if we say velocity of P2 with respect to P1 in rod frame, that is 0. But now suppose we take the relative velocity of P2 with respect to P1 in ground frame. Okay. See what we'll get here. P2 P1 in ground frame. Velocity of P2 with respect to P1 in ground frame. See, in ground frame, P1 and P2 are not static. P1 and P2 are moving in circles of respective radiuses L1 and L2. So velocity of P2 with respect to P1 in ground frame will be equal to velocity of P2 in ground frame minus velocity of P1 in ground frame. Alright, velocity of P2 in ground frame will be omega into L2. Omega L2 vector. L2 vector is the vector from pivot to point L2. This is the vector L2. And Vp is circular motion result. This follows from the result of circular motion. Point moving in a circle of radius r. Speed of point P is omega r. Similarly, Vp1g P1 also moves in a circle with respect to ground whose center is at the pivot and radius is L1. Angular speed is omega. So P1G will be omega L1. Now you can see that this is equal to omega into vector L2 minus vector L1. Alright. And this you can see that this is non-zero. So if we take the velocity of P2 with respect to P1 in rod frame, it is 0. And if we take the velocity of P2 with respect to P1 in ground frame, it is non-zero. So if we don't specify the name of the frame, we simply say Vp2 P1. Will it have any meaning? Tell me. It will have no meaning. You have to specify that which frame you are taking the velocity difference in the two velocities. Without specifying that frame, there is no meaning. Because in rod frame, this quantity is 0. In ground frame, this quantity is non-zero. So if you write only this much, it has no meaning. But when you specify the name of the frame, then it becomes a meaningful concept. Is it alright? So whenever we take the relative velocity between 2 points, velocity V2 minus V1, we should specify with respect to which frame V2 and V1 are being taken. Then the relative velocity between 2 points becomes a meaningful concept. If you don't specify the name of the frame, it is meaningless. But see, in elementary books on 11th appearing books, this is not written because it is not expected that you will know it in class 11th. But still, if you understand this concept, it is better. It is implied that in most of the 11th books, plus 2, 11th, when you passed class 10 and appear in 11th, whatever board it may be, it is implied that these velocities are in ground frame. In majority of the cases, relative velocity is in ground frame. They don't specify the name of the frame. But actually we should specify because without that it is meaningless. It is vague. It has no meaning. So this I have told you. So suppose that instead of rod and ground frame, we take some other frame. Then again V2, Vp2 and Vp1 in that frame will not be same as 0 or not be equal to this much. It will be something else. So this becomes clear. What I am telling is that you should specify that in which frame you are taking the velocities. Okay, then it becomes a meaningful concept. Okay. This I'll rub it off. Actually, we'll see ahead in coming more videos. We'll see that relative velocity between 2 points is same in all frames which are in mutual translation. There, the relative velocity between 2 points becomes same in any two mutual frames which are in mutual translation. There, the relative velocity will be same. We'll see in coming videos. Okay. So now our aim is to just show how the velocities of a point in two different frames are related to each other. Okay, that exact relation we have to find out. For that you should know that on 10th video, it was discussed that for any vector A, dA by dt in frame F is equal to dA by dt in frame M plus omega cross A. This was shown in the proof of this was given in the 10th video, where A is any arbitrary vector, F and M are two frames, omega is the angular velocity of M with respect to F, and A is any arbitrary vector. This was fully derived in the 10th video. You can go through the 10th video and there the proof will be given. Okay. So now see, this concept will be used here. Okay. So, and omega is the angular velocity of M with respect to F. And omega is defined to be the rate of change of orientation with respect to F. That is the angular velocity of M with respect to F. So now see, this is the frame F. Okay. This is the frame M. O is the base location of frame F. O is a fixed location, real or imaginary location of frame F. Fine. And capital A is the real or imaginary location of frame M. And P is an arbitrary moving point. Okay. This is the situation at time t. Omega is the angular velocity of M with respect to F at certain instant t. Alright. O to P vector is RPF. This is a vector or a position vector of P at time t. O to A is RAF. This is nothing but the position vector of A with respect to O in frame F at time t. And A to P is RPA, relative vector from point A to point P at time t. So now we can see from the triangle log that this is equal to this plus this. So RPF is equal to RAF plus RPA. Okay, this equation is valid for all times. Since it is valid for all times, we can take the time derivative of this equation. So this will be drpf by dt in frame F will be equal to draf by dt in frame F plus drpa by dt in frame F for all times. Now this quantity drpf by dt in frame F is nothing but vpf, and draf by dt in frame F is nothing but vaf, velocity of point A with respect to F, where A is some real or imaginary location of frame M. Alright, plus drpa by dt in frame F. Now how do we write drpa by dt in frame F? See, vector rp originates at A, its tail is at A and head is at point P. But A is fixed in M, not in F, and here derivative is taken in frame F. So what we apply? We apply this formula to this vector. Instead of vector A, we take vector RPA. Instead of vector A, we take the vector RPA. So dA by dt in frame F is equal to dA by dt in frame M plus omega cross A. So drPAF by dt in drPA by dt in frame F is equal to drPA by dt in frame M plus omega cross RPA. So for this we replace this two here. So drPA by dt in frame F is equal to drPA by dt in frame M. drPA by dt in frame M plus omega cross A. Instead of A we write RPA. Omega cross RPA. ये देखिए. All right. Fine. So VPF बराबर is equal to VAF plus. Now what about drPA by dt in frame M? This is nothing but the relative velocity of P with respect to A in frame M. Just now as I discussed, dr by dt in frame F is equal to Vp2F minus Vp1F. So drPA by dt in frame M will be written as Vpm. See, drPA by dt in frame M will be written as Vpm minus Vam. This is M, okay? Plus omega cross RPA. Is this one clear? drPA by dt in frame M will be written as Vpm minus Vam. That same vector theory which we discussed just now. P1 and P2 are two moving points. R is the relative vector of P2 with respect to P1 at time t. There we discussed that dr by dt in frame F, that is equal to Vp2 P1F, velocity of V2F minus V1F. So dr, instead of vector R we have vector RPA. So drPA by dt in frame M will be written as Vpm minus Vam. Alright. Now A is the location of M, real or imaginary location of M. So Vam becomes 0. So this term goes away. So VPF बराबर क्या will be equal to what? VAF plus क्या? VAF plus VPM. VAF plus VPM plus omega cross क्या? RPA. ये देखिए, this is the relation. So VPF is equal to VAF plus VPM plus omega cross RPA. So this is the relation between velocities VPF and VPM. So this is one formula which should be remembered. Okay. So one relation we have obtained. So VPF is equal to, I am writing VPM first, commutative law of vector addition. Terms can be interchanged, no problem. So VPF is equal to VPM plus VAF plus omega cross what? RPA. So VPF is equal to VPM plus VAF plus omega cross RPA. Okay. So this is the relation between VPF and VPM. VPF is equal to VPM plus VAF plus omega cross RPA. So this is the relation between velocity of a point P as seen from two frames M and F which are in mutual rotation. Expression for velocity relationship between velocities of point P between two frames F and N which are in relative rotation with respect to each other. So VPF is equal to VPM plus VAF plus omega cross RPA. Fine, alright. Now our aim is to find the expression for acceleration relationship between acceleration of point P as seen from two frames M and F which are in mutual rotation. This I'll rub, okay? So now we have obtained this relation. VPF is equal to VPM plus VAF plus omega cross RPA. Alright. So this vector equation is valid for all times. For all times this vector equation is valid. Now what we do, we differentiate this equation with respect to time on both sides. This means for all time, okay? So we write like this: dvpf by dt in frame F is equal to dvpm by dt in frame F plus dvaf by dt in frame F plus d by dt of omega cross RPA in frame F. Now this quantity dvpf by dt in frame F is nothing but APF. Now how do we write this formula? For that we apply this formula here. Instead of vector A we take vector VPM and F and M. So this will say as dvpm by dt in frame M plus omega cross VPM plus this will be nothing but AF, acceleration of location capital A of M with respect to frame F. And now this term will derive by using the product rule of calculus, but this is a cross product, so order of the terms has to be maintained. We cannot change the order of the terms, so we'll write it as, from product rule of calculus we'll write it as d omega by dt in frame F cross RPA plus omega cross drpa by dt in frame F. So we get APF is equal to this quantity is nothing but APM plus this is omega cross VPM and this is AAF. This is equal to beta. D omega by dt in frame F is nothing but the angular acceleration of M with respect to F. So beta cross RPA plus omega cross drpa by dt in frame F. Now drpa by dt in frame F we'll write in same way as we did in case of velocity. So if we apply this formula here, instead of vector A we take vector RPA. So we just say and F and M. So drpa by dt in frame F will be written as drpa by dt in frame M plus omega cross what? RPA. drpa by dt in frame M plus omega cross RPA. drpa by dt in frame M plus omega cross what? RPA. Alright? Is it clear? I'll rub this, okay? So now we get the relation APF is equal to APM plus omega cross VPM plus AAF plus beta cross RPA plus omega cross drpa by dt in M is equal to VPM minus VAM. From the definition of relative velocity between 2 points, VPM minus VAM plus omega cross RPA. Now VAM becomes 0 because point A is a real or imaginary location of M, so it is fixed with respect to M, so VAM becomes 0. So we get APF is equal to APM plus omega cross Vpm plus AAF plus beta cross RPA plus omega cross Vpm plus omega cross RPA. Alright, so we get, now I rub this, okay, this I'll rub it, okay, fine. APF is equal to APM. We rearrange that order of terms. APM, we write this term as first AAF plus beta cross RPA, omega cross VPM, to 2 omega cross VPM, 2 omega cross VPM plus omega cross RPA. Alright, so we get APF is equal to APM plus AAF plus beta cross RPA plus 2 omega cross VPM omega cross RPA. So see, this is the general relationship between acceleration of point P as seen from two frames M and F which are in mutual rotation. This formula. And velocity relation we have already derived, and I'll write it here again. So VPF is equal to VPM plus VAF plus omega cross RPA. So these are the two relations. This is the relationship between velocity of point P as seen from two frames M and F which are in mutual rotation, and this is the relationship between acceleration of point P as seen from two frames M and F which are in mutual rotation. Alright, fine. I'll rub this one, okay? Now we take the special case. We take the special case now, that suppose M translates with respect to F. Suppose M translates with respect to F. Now what is omega? Omega is the angular velocity of M with respect to F, and that is equal to rate of change of orientation of M with respect to F. Now if M translates with respect to F, then from the definition of translation, as was discussed in the first, third or fourth video of this relative velocity, it was clearly stated that when M translates with respect to F, then orientation of M with respect to F doesn't change. This means rate of change of orientation of M with respect to F is 0. That is, angular velocity of M with respect to F is 0. So omega is 0 for all times. And if omega is 0 for all times, that means omega is a constant, and derivative of constant is 0. So therefore, d omega by dt in frame F, that becomes, which is nothing but beta angular acceleration of M with respect to F, that also becomes 0 for all times. Fine. Now see, in this case, one more thing should be noted. If M translates with respect to F, then that any location of M has same velocity with respect to F. So in that case, this was also discussed in the theory of translation and rotation chapter. Third or fourth video of relative velocity, you can go through it and see it. Okay. So M translates with respect to F, then omega and beta both become 0 for all times, and this VAF becomes VMF. You should know why. VAF is replaced by VMF. Why so? Because when M translates with respect to F, then all locations of M have identical velocities with respect to F, and that velocity will be denoted as VMF. And one more thing, if M translates with respect to F, then all locations of M have identical acceleration with respect to F. So AF will be written as AMF, acceleration of M as a whole with respect to F, and VAF will be written as VMF, VMF meaning velocity of M as a whole with respect to F. So if we make these substitutions in this equation, So what will happen? VPF will be equal to VPM plus VAF becomes VMF plus omega cross RPA. Omega is 0. Omega 0 cross RPA. So 0 cross RPA becomes 0. From the theory of vectors, cross product of two vectors, this term goes away. So VPF is equal to VPM plus VMF. This is the relationship. So VPF is equal to VPM plus VMF. ये हो गया. This is the relation between VPF and VPM as seen from two frames M and F which are in mutual translation. And what about acceleration? If M root translates with respect to F, in that case beta goes away, omega goes away, this also goes away, 0, and AF is replaced by AMF. So this equation becomes APF is equal to APM plus AAF. AAF becomes AMF plus beta cross RP. Beta is 0, so 0 cross RPF 0. Omega is 0, so 0 cross VPM 0. 0 cross RP will be 0, that is also 0. So 3 zeros in 0. So that means we get APF is equal to APM plus AMF. Alright. So this is the formula which we get in case of translating frames. Okay. And this is a general relation. These two are general relations. And from this translating frame, the results are just the special cases of these two more general relations. Fine. So in this video I have fully explained how velocities and acceleration of point P are interrelated in two frames which are in mutual rotation and in two frames which are in mutual translation. This is all about this in 13th session. In the 14th session, what we'll do, we'll take up some numericals on general rotating frames. We'll carry out the calculation for these two formulas. Alright. So I hope this is fully understood. You should definitely go through it. See, if you are preparing for JEE Advanced, definitely you must know about it. You must have a complete idea because it's a very fundamental concept. You cannot leave it. You should not have a half-baked knowledge on it. You should have complete knowledge and full knowledge. Because, see, invariably these concepts appear in some or other numerical. So you should know it fully. That's what I'm telling you. You should not know this only in half, but you should know it fully. That's very important. Okay. So it will help you a lot in JEE Advanced in clearing a concept, and it will greatly enhance your problem solving ability in JEE Advanced if you know these two results for rotating frames. And they are extremely important, as we'll see. These concepts, they are extremely important in concept building for mechanics. Okay. So they should be known fully. So that's why I'm telling it. I'm repeatedly emphasizing it. You should definitely know these two formulas. Alright. So now we close it. Okay. Now we'll continue in the 14th session. We'll carry out the exact numerical calculations. Fine. Let's close it. Okay.